Hello everyone, welcome to this session. In this session, I'm going to show you one example as to how to use data envelopment analysis. So let's go through this. So the story is called the five branches. Now, what is DEA used for? DEA, data envelopment analysis, is used to find out which of the options are truly efficient. So in this case, we are talking about a bank which has five different branches, and we have data on the inputs and outputs. Out of these five branches, which are the efficient branches? So that's what we are trying to find out. Let's get ahead. Now, let's say you are heading the operations for a bank in India and you have five branches. And the question that you are asked every quarter is which branch is most efficient and who are the underperformers and what are they doing wrong? Okay. So now let's say you have this particular option with you. So you have these five branches, this data is available to you. You have branches A to E, you have full-time employees, that is the staff. You can see that on the screen. You have the cost in rupees lakhs, and you have loan numbers, number of loans, and you have deposits in crores. Now, here we are considering that you have two inputs, number of employees is an input and the cost is an input, and you have two outputs. So we're talking about a situation where you have multiple inputs and multiple outputs. Number of loans is an output and amount of deposits. The rupee amount, rupees in crore, amount of deposits is the other output. Now, looking at this, again, going back to the previous slide, if you see, now, would you consider the biggest output branch as the best branch? So branch D is the biggest branch in terms of number of loans. 160 loans are processed, but it uses 10 staff members, whereas there are branches which have lesser number of staff members, and the cost is 28 lakhs. Will you consider the lowest cost as an option? Lowest cost branch as an option. Branch C, it has a cost of rupees 12 lakhs, but the output is also less. So can you consider these two as the best or most efficient branches? The answer is no. What we need to look at is the ratio, best output versus input. But best output versus input works when you have only one input. But here you have multiple inputs. With two inputs and two outputs, there is one option which is to use data envelopment analysis. And we'll look at that how. Now, out of these, if we see the scores, now I'm showing you the output first. This is the DEA score, data development analysis score. So we see that branch A has a score of 1, branch B has a score of 0.9, branch C has a score of 1 again, branch D is 0.686, branch E is 1. Now, if you just look at this, branch D has the highest number of loans, 160, and it has the largest number of FTEs, but still it doesn't have a score of 1. So in this case, a score of 1 means it is on the efficiency frontier. Any branch which has a score of 1 is on the efficiency frontier, and the branches which scores less than 1 are at, for example, branch B is at 0.9, it's at 90% efficiency. Branch D is a 68.6% efficiency because the score is 0.686. I will go through the mechanism of this. Now, so what is it that DA is trying to achieve? So what we are trying to answer is, can any blend of the other branches, any combination of any other branches can produce at least this much output as the best branch? Any combination, any blend of other branches, can it produce as much output as the best branch or as this branch whenever we are comparing this branch? Okay, so it should be able to achieve that output with strictly fewer inputs. Only then the efficiency will be high, right? Efficiency is output by input. So can it achieve the same output at least with lesser number of inputs? If that is not the case, so again, going back to our example A, B, C, D, and E. So if we are considering branch A, and we see that there is no other branch which can produce as much output as branch A with lesser number of inputs, then A will get a score of 1. So if it scores 1, it is 100%, which means it's on the efficiency frontier and it is good or it is the best in terms of efficiency. If the answer is yes, there are other branches or there is a combination of other branches which produce the same number of output or same amount of output with less number of inputs, then the score for that branch is less than 1. And that's where we need to see what can be improved to make it the best. Okay, so that is what we are trying to address or trying to answer here. Now let's understand the mathematics behind this. So here we are trying to find out the optimus. We are trying to optimize, right? We are trying to optimize, and like any optimization problem, we have an objective function which is to minimize theta. When we are minimizing theta, theta is what? Theta is the efficiency score. Theta is the efficiency score which we are trying to minimize. Now, be careful about this. For every branch, we will have a linear programming problem. We'll have an LP for each branch. So since we have 5 branches, we'll solve it 5 times and then we'll get the complete picture and you'll also get the efficiency scores. And then we have the constraints. We have the input constraints. So input constraints are this. Weight given to a peer branch is lambda. And we are trying to see that it is less than, the inputs are less than the branch that we are testing. Similarly, the output should be at least what the output is for the branch that is being tested. Okay, if the output is more, good, but if the output is less, that's not what we want. And all these things should be non-negative. So non-negativity constraint is there. Okay. Okay, now let's understand theta again, right? Let's understand theta. What exactly is theta here? We are trying to minimize theta, right? So it is the proportional factor by which a branch could shrink all its inputs. So let's say theta is 0.9. So if we shrink all the inputs by 0.1, make it 0.9. If we reduce the full-time employees by 0.1 and we reduce the operating cost by 0.1, by producing the same amount of output or more. Okay, so that's what we are trying to minimize. So this is theta. Theta is, to repeat, is a proportional factor by which a branch could shrink all its inputs, which in this case is staff FTEs, full-time employees, as far as staff is concerned, and the operating cost. If it can reduce by, let's say, 0.1, we are working at 90%. So that's what we are trying to get here. Okay, now let's look at again, we'll go back to the original. So when we look at the table again, first we need to find out the ratios, right? So here we are finding the ratios as in loans per staff member, loans per unit of cost, deposits per unit of staff, deposits per unit of cost. So here we see, so this is a simple calculation, total amount of loan divided by number of staff, we get 25, we get 8.33. Now, key insight is each efficient branch is good at one of the ratios. At least one ratio, it is the best. So if you look at branch C, its loans by staff ratio is 25, which is the highest, and also its loans per unit of cost 8.33 is also the highest. So branch C ranks number 1 or ranks well. Similarly, branch E has the deposit per unit of cost. Deposits per unit of cost is 1.63, which is the highest. So we can consider branch C and branch E as very, very good or as being efficient, right? Whereas other branches, branch D, if you look at branch D is the lowest in all the cases. So branch D currently is lowest in all these options as of now. Now, when we looked at the previous table, we saw that branch C scores 1, right? Branch C scores 1. So how do we check? We see that is there a combination or is there any other branch which can beat branch C in terms of output with lesser number of input. So to match C's 100 loans, C has 100 loans, right? And the amount is 18 crores, but they have only a staff strength of 4. So if any branch has a staff strength of less than 4 and is still able to make 100 loans, it will beat branch C. But is that happening? Branch A, loans per staff is 24. It can't beat C. B can't beat, D can't beat, E can't beat. So all these branches on their own can't beat branch C. When I say beat branch C, I mean they cannot be in a situation where their output is matching C. Output is at least matching C with less than 4 staff. Okay. So this means branch C scores a perfect 1 in this particular case. Now branch E, why branch E scores 1? Now branch E is interesting. We have 130 loans. The number of loans is 130. The deposits is 26 crores. Cost is 16 lakhs and staff is 6. Now, if we have to compare branch E with branch C, now let's multiply all the inputs and outputs of branch C by 1.5 so as to make it comparable, because branch C has 4 staff members, whereas branch E has 6. So in order to make 4 equivalent to 6, you have to multiply by 1.5. When we do that in this table, as you see in this table, you will find in this table, you will find that staff is 6 in this case, but the cost becomes more than 16 lakhs. Number of loans have increased, number of amount of deposits have increased. But the problem is cost is also increasing, right? So we can't do that. So E doesn't score better than C because when we make the staff strength the same, the costs have increased further. Yeah. So that is the issue here. Now, why branch A scores 1? Now, A is not the best in any of these, but here we need to understand the subtlety here. Now, what we could do, we could look at scaling up branch C by 1.2 times. So if we do that, 1.2 into C, you see 4.8. Staff becomes this 14.4 lakh, 120 loans, but its deposits are 21.6 crores. Okay, so deposits are less than branch C. So this scaling won't help, right? This scaling up of branch C won't beat branch A. Similarly, using branch E, so the number of staff is 6, A is 5. So if we see only 108 loans, if we do the same thing here, right? So even E can't do that, right? So this also fails. And third could be a blend of C and D. Blend of C and D. When we blend C and D, we find that the staff ceiling pulls it down and deposit needs pushes beta up. So this becomes infeasible. If you blend C and D, that also becomes infeasible. So this doesn't work. So what we come to finally is branch C is the loan champion because it has 25 loans per FTE and 8.33 loans per rupee lakh. Branch E is the deposit champion and branch A is the scale position because it has a unique deposit plus loan balance and no other combination can beat it. Okay, simultaneously it can't be beat. Now branch B. Now if you look at branch B, this is the value that we have, staff 8 and this. Super C, if we multiply branch C by 1.5, we see that branch C dominates, right? Branch C is better. So what we can do is we can improve branch B by reducing the staff by 10%. So there's something called a radial contraction. So if we reduce by 10% or make it 0.9, we get 7.2 FTEs. 7.2 FTEs. cost becomes 18 lakhs, and then we remove the slack here. We remove the slack here. How? 7.2 FTEs is what we are getting here. And branch C has 6, so 7.2 minus 6 is 1.2. So finally we get 6 FTEs, and cost slack, if we reduce, then you don't have any change. So this is what happens here. Now let's look at the solution here, right? So this is what we see, that this is what we saw on that slide. So when we calculate this, what we find is that we had branches A, C, and E on the efficiency frontier. We had branches A, C, and E on the efficiency frontier. They were 100%, and branch B was at 0.9, which is 90%. There's a 10% waste, and D was at 0.686%, right? There was a 31.4% waste. Now let's look at how did we arrive at this number mathematically. So what is the staff constraint here? Staff constraint here is constraint is 4 into 1.6. We make it 6.4 less than or equal to 10 times theta d. So when we have to find theta d, we'll divide 6.4 by 10. It is 0.640. Okay. Now we also have to look at the cost constraint. So we have to multiply this 12 also with 1.6, which we get as 19.6, should be less than or equal to 28 times theta d. So when we solve for theta d, 19.2 divided by 28, we get 0.6857. We get 0.6857. Okay. Now, when we round this off, it becomes 0.686. And that's how this 68.6 came here. 68.6 was achieved using this. 68.6 was achieved using this, right? By solving the inequality, So what we need to do, we need to reduce the number of FTEs, okay, and try to improve the output. So that's the bottom line. That's the bottom line here. So this is how you do data envelopment analysis, and there are tools available which will solve it directly for you. Thank you very much.